The screencast for worksheet 15 on alcohol, carboxylic acids, and esters. Question 1 on discussion questions. Give the IUPAC name of the following substance. I think this question is quite straightforward. Again, how to name, look for the stem. Then, identify the substituents that you have not accounted for in the stem. The most important group here, and there's only one functional group, which is the hydroxyl functional group, so it's the alcohol. So it is proper on the second position, 2 nor. Okay, next we have 4 carbon and it's a acid group. So very straightforward, it's just butanoic acid. Next, when they give the structural formula, it's slightly harder to identify the name. So what I would recommend you to do is to draw it out. So first, 1 carbon, second carbon. Now you know that this carbon is bracketed out, so which means that it's a substituent of the previous carbon. So that's why I draw this CH3 group here bonded to the second carbon. Then next carbon, then the last carbon is a COOH group. Okay, so how do we name this? The most important group is of course the acid group. So there's 4 carbon in the longest chain, so it's butanoic acid. And how do we name the methyl? No, we do not name it as the second 2-methyl. The most important functional group here is the acid. That should always be the first position. So it's at the third position. So it's 3-methyl butanoic acid. Next, we have ethyl butanoate. 1, 2, 3, 4. 1, 2, 3, 4. Before we encounter the COO group. COO group. Next, we have the 2 other carbon. Okay, that's why, how do I name this? You must first be able to split it into a acid and the alcohol part. Okay, the part with the C double bond O is the acid group. Therefore, we name the alcohol first. There's 2 carbon, so it's ethyl butanoate. Next, assignment question. Question 2. Tartaric acid is an organic acid that can be found in grapes, lemons, and oranges. Yes, this structural formula. What is the empirical formula of tartaric acid? Very simple. Write down the molecular formula first. It's C4H6O6. Therefore, its empirical formula will be C2H3O3. Now, tartaric acid contains 2 functional groups. What are the functional groups present? And what is the chemical test to distinguish between these 2 products? So the 2 functional groups are the hydroxyl functional group as well as the carbonyl functional group. Okay, after you state the functional groups, you must tell me what is the test to distinguish between these 2 functional groups. Okay, we can use a acid carbonate or an acid metal reaction. Okay, these are specific towards a organic acid, which is your carboxylic acid. Okay, so note that the litmus test is not considered as a chemical test, as well as testing it with universal indicator. C, we have a mole calculation question. 23.5 cm³ of 0.2 mole per dm³ of sodium hydroxide solution was used to neutralize 25 cm³ of tartaric acid extracted from grapes. What is the concentration of tartaric acid? So, for this question, you must first know what is the basicity of this acid. As you can see, there are 2 acid groups. That means there are 2 acidic hydrogen as boxed up in red. Since there's 2 acidic hydrogen per molecule of tartaric acid, it is a dibasic acid, which means that for 1 mole of tartaric acid, I need 2 moles of NaOH to neutralize it. First, we find the number of moles of NaOH. Take the volume times concentration. Volume times concentration, this is number of moles. Then the mole ratio is 2:1. Therefore, tartaric acid, the number of moles will be divided by 2 to get this answer. Hence, concentration will just be number of moles divided by volume, and you get 0.094 mole per dm³. D, tartaric acid and its compounds have many uses. This salt is made from sodium carbonate and potassium hydrogen tartarate. Carbon dioxide and water are the other products formed in this reaction. So write an equation for this reaction. Okay, so you must, this is like this comprehension. you must know what it's made of. So these two are your reactants. And what are your products? Your product is this, as well as carbon dioxide and water. So with this information, you are able to write down this equation. Then you just balance the equation. Okay, 1 mark. What is the potassium hydrogen tartarate acting as in this reaction? Okay, so you see that we have a carbonate, we have a salt, and we have water and carbon dioxide. So what is this reaction? It's actually an acid-carbonate reaction. So potassium hydrogen tartarate is acting as an acid. Citric acid is another organic acid that's found in grapes, lemons, and oranges with this structural formula. A solution of sodium hydroxide is titrated against tartaric acid and citric acid respectively. Deduce the ratio of volume of sodium hydroxide used in both titration if the volumes and concentration of both acids used were the same. Okay, so this is a test of the basicity. Because concentration, volume same, number of moles is the same, then assuming that they have the same strength. Okay, so let's look at this. There are 3 acid groups here, which makes it tribasic. Okay, if you recall, tartaric acid, as we said here, is dibasic. So for 1 molecule of citric acid, I need 3 moles of, for 1 mole of citric acid, I need 3 moles of NaOH. For 1 mole of, what's the other acid? Tartaric acid, I need 2 moles of NaOH. So the ratio of the NaOH used in titrating will be 3:2. Next, when acidified potassium dichromate 7 was added to another organic compound and warmed, citric acid was formed. The acidified potassium dichromate turned from orange to green. What type of reaction has occurred? It is oxidation or redox. You know, because the acidified potassium dichromate turned from orange to green. This is an indication that it has been reduced. Okay? So since it is reduced, the compound is oxidized to form citric acid. So what is the compound before it is oxidized? We have only learned about the oxidation of alcohol to carboxylic acid. Okay, since here we see that there are 3 acid groups, therefore here there should be 3 hydroxyl group as highlighted. Now note that there's this hydroxyl group that did not react. So do you know why this hydroxyl group did not get oxidized? Okay, note that only primary alcohol can be oxidized into carboxylic acids. What do I mean by primary alcohol? It is when the carbon that the hydroxyl group is attached to is only attached to one other carbon. Okay, so this is known as primary. If the carbon that the hydroxyl group is attached to 2 other carbon, then this is known as secondary. If the carbon that the hydroxyl group is attached to 3 other carbon, this is known as a tertiary alcohol. So with respect to that, can you tell me, for this hydroxyl group, is it primary, secondary, or tertiary? Okay, you should see that this carbon is attached to 3 other carbons. So this is a tertiary alcohol. Okay, if it's a tertiary alcohol, it will not get oxidized because the carbon that is attached to, right, already formed 3 other bonds with 3 other carbons already. So it cannot form any more bonds with the oxygen. Okay, so note that only primary alcohol can oxidize to carboxylic acids. Part 3, when the bottle of wine is left open for too long, the reaction that occurs is the same type as that of E part 1. E part 1 being this one. Okay? I think they mean F part 1. Explain briefly the cause of the reaction. Okay, the alcohol is oxidized by atmospheric oxygen in the presence of bacteria. Yeah, that's just it. Okay, nothing to explain. Okay, G methyl-butanoate is an ester with a fruity odor of pineapples. Describe how you can synthesize methyl-butanoate from butene. Write the chemical equations and reaction conditions for all the steps involved. Okay, this is what we call a retrosynthesis question. So they tell you what you want, the end product that you want, and they tell you your starting material. So you are to derive the steps that you must take to get to the end product given your starting product. Okay, it is always easier to start from what you want at the end. Okay, then you break it apart. For instance, if I start with methyl-butanoate, I draw it here. Methyl-butanoate. I know that it is made of butanoic acid as well as methanol. Let me just use another color. Plus methanol. Okay, so I know since this is butanoic acid and I started out with butene, 4 carbon, 4 carbon, it must mean that my butene must somehow become the butanoic acid, right? So what is connecting these two? You can look at your reaction map. You should see that from an alkene to become an carboxylic acid, it must pass through alcohol. So what I can do is I can make it into an alcohol. Then I will get back to my starting material. So this is what we call retrosynthesis, where you have the end product in mind, you break it up, and think of how do you get back the starting material. Okay, so then we can work out the steps in this manner. Okay, so from butene to butanol, what is the step? We can just do addition of steam. So to recall addition of steam, this is the condition. Okay, then from here, from alcohol, how do we get carboxylic acid? We oxidize it with either acidified KMnO4 or acidified K2Cl2O7 to form butanoic acid. From there, how do we get the ester? We react the acid with methanol to form methyl-butanoate. The condition will be with concentrated sulfuric acid. Okay, question 3. The apparatus used to measure the boiling points of mixture of organic liquids are drawn below. There are two versions, one using a side arm, the other using a flask with two necks. H is the inlet for inserting the thermometer. Okay, draw an X at the cross at the points where the bulb of the thermometer would best be placed in both diagrams. So we want to measure the temperature that it will just nice leave the flask. Okay, so for here, the thermometer is put in here. Since the vapor will move this way, okay, we want to measure the point at where it just goes into the pulp. Okay, it is not possible for the thermometer to measure the temperature at this point because thermometer is straight line. Okay, so the max it can do is measure here, whereas here thermometer is a straight line. It can measure directly at the point of entry, okay, into the condenser. What is the reason for using the water condenser? Okay, two reasons. One, prevent hazardous fumes from escaping into the atmosphere. Two, to prevent loss of volatile organic substance. Okay, because we don't want the unreacted organic reactants. Okay, so anything that's reacting here, right? We don't want it to be lost, and if it's lost to the atmosphere, then your yield will be lesser. What we want is, even if it vaporizes, we want to condense it back. Okay. B, the bonding points of different mole fractions of proper 1 nor and proper 2 nor are shown in the graph below. Okay, you may not know how to interpret this kind of graph, so let me just explain over here. Okay, now you note that the x-axis is the mole fraction of proper 1 nor. Okay, what does it mean? When the mole fraction of proper 1 nor is 0, it means that there's no proper 1 nor. Since it's a mixture between proper 1 nor and proper 2 nor, it implies that what is left is all proper 2 nor. Okay, conversely, if the mole fraction of proper 1 nor is 1, it means that it is 100% proper 1 nor. There's no proper 2 nor at all. So you can see that when we add proper 1 nor to proper 2 nor, there is an increase in the boiling point. What type of intermolecular attraction is there in this mixture? Again, because it is alcohol, OH and CCCOH, they both can undergo hydrogen bonding. Therefore, the main type of intermolecular attraction in this mixture is hydrogen bonding. Using the information from the graph, what are the boiling points of proper 1 nor and proper 2 nor respectively? How can we tell? Okay, at a point when it's 0, it is 100% proper 2 nor. Therefore, I can tell that this is the boiling point of proper 2 nor, which is 82, I think. Here will be the boiling point of proper 1 nor, which is 98. Okay, why is the boiling point of proper 2 nor lower than that of pure proper 1 nor? Okay, if we look at the structure, here we can see that this is more linear, whereas this is kind of branched. Okay, it's not correct to say that it is like a branch alkane. Yeah, so but you can see that since this is branch, this is more spherical. Okay, so there's lower surface area as compared to this. Okay, they both have hydrogen bonding, so hydrogen bonding is not a factor here. The factor becomes the van der Waals forces. Okay, so remember, other than hydrogen bonding, it is on top of van der Waals. Okay, so they both have hydrogen bonding plus van der Waals. Since they have the same number of hydroxyl groups, hydrogen bonding is not what is causing the difference in the temperature. So what is causing the temperature is the strength of van der Waals forces. So we can explain it in terms of the surface area. Okay, this part is a bit iffy. So instead of writing this, you can say as the shape of proper 2 nor is more spherical, okay. Now, part C, when mixtures of ethanol and cyclohexane are used, the boiling points are as follow. Okay, so this time it is between ethanol and cyclohexane. Okay, again, ethanol looks like this. Cyclohexane looks like this. Okay, so you can see that a very visible difference is that this one there's one hydroxyl group, whereas for cyclohexane there's none, and also that cyclohexane is a lot larger than ethanol. Okay, so the mole fraction of cyclohexane On the grid, plot the boiling point and mole fraction curve. So this one you just read and plot lah. Okay, so you can see that when there's no cyclohexane, the boiling point of ethanol is around 78. Okay, when it is 100% cyclohexane, the boiling point becomes about 80. Okay, based on the boiling curve in C part 1, comment and suggest an explanation for the type of molecular interaction that takes place between ethanol and cyclohexane. Now you may be thinking, what is this question asking me to do? Okay, so you can see that it's very strange in the sense that there's this downwards curve, then it curves out again. Okay, the lowest point is when it's around 0.5, 50-50 mixture. Okay, so why is it that their boiling point decrease when it's a 50-50 mixture? What does this suggest about the type of interaction between the two types of substance? Okay, it is a U shape. So first, you'll need to comment on the data given. So what is unusual about this data is that the shape is U shape with a minimum boiling point at 0.5 mole fraction of cyclohexane, or you can say 0.5 mole fraction of ethanol. So what does this suggest about the type of interaction? First, if it's between ethanol and ethanol, there can be hydrogen bonding plus van der Waals. Between cyclohexane and cyclohexane, because they are both very big, they have strong van der Waals forces. I mean stronger than the van der Waals forces in ethanol. But since ethanol has hydrogen bonding, therefore the intermolecular forces is also quite strong. But what happens if they mix together? If they mix together, can there be hydrogen bonding between cyclohexane and ethanol? So there's no hydrogen bonding. And what about the strength of the van der Waals forces? Will it be as strong as between two cyclohexane molecules? No, because this molecule is very small. Okay, look at here again. This is huge, okay, relatively big, and this is quite small. So the van der Waals forces here is a weaker van der Waals as compared to between cyclohexane. So this is why when it's a mixture, the interaction is a weaker type of interaction. Okay, this is what the data suggests. Okay, so the minimum point tends to suggest that the molecules in the mixture have a greater tendency to escape from the pure. Okay, so what you can tell is that when it's a mixture, the van der Waals forces that's present is weaker. Let me just write it down. The strength of van der Waals between the cyclohexane molecules and ethanol is weaker than the H bonding between ethanol molecules and van der Waals between cyclohexane molecules. Okay, so again, here between ethanol and ethanol, there's hydrogen bonding which is stronger than van der Waals forces. Here, between cyclohexane molecules, they have strong van der Waals forces due to large size, okay, bigger surface area. Okay, but between the two types, first of all, there's no hydrogen bonding. Second of all, it's a weaker van der Waals as compared to between cyclohexane. Therefore, since the overall strength of the intermolecular forces decreased, it has a lower melting and boiling point. What observations could be made when mixing together 50 cm³ of each ethanol and cyclohexane at room temperature? Okay, this answer, the first one, is a bit strange. Ignore. Okay. There's an increase in the volume of the mixture, and there is 2 layers formed. Or you can write that they are immiscible. Since they do not form suitable interactions with each other, you should see that it forms 2 layers. Okay. Now, you may ask, since it forms 2 layers and is immiscible, why is there an increase in volume of the mixture? Okay, according to the setter, he said that this is 50 cm³, this is 50 cm³. So 50 cm³ become 100 cm³. So there's an increase in the volume. Okay, now how do you know you have to write this? Actually, I also don't know you need to write this. But exam we will not set this kind of question, so don't worry. Okay, but you should know that there are 2 layers being formed and they are immiscible because they don't have suitable interaction formed with each other. As mentioned before, light dissolves light, so polar substances dissolve in polar solvent, non-polar substances dissolve in non-polar solvents. Since cyclohexane is non-polar and ethanol is polar, they do not dissolve in each other. Okay, enrichment, classification of aliphatic alcohol. Okay, so this is what I mentioned just now. If it's a primary alcohol, the hydroxyl group is attached to, the carbon that is attached to is only attached to one other carbon. Okay, the carbon that is attached to is only attached to one other carbon. Secondary alcohol, the carbon that is attached to 2 other carbons. Okay, the carbon is attached to 2 other carbons. Same goes for, okay, the alignment is a bit weird. Okay, it should be aligned here. It's attached to 2 other carbons. Tertiary is attached to, the carbon is attached to 3 other carbons. Aliphatic polyhydrate alcohol contains more than 1 OH group, so we call it a diol or a triol. Exercise. Draw the full structural formula of all the structural isomers of alcohol with the molecular formula C4H9OH. Classify them as primary, secondary, or tertiary alcohol and give the IUPAC name of each. So this is the answer. Okay, if you have any more questions about this set of worksheet, you can ask me on next week's lesson. Okay, thank you.